Hello. So we are in we have so far just cleaned up code and refactored stuff in preparation for creating the make map command, which is supposed to show the mapping of character codes that you type on the keyboard to the kana or kanji that they correspond to. And so far, we're getting pretty close. And to recap, there are two there are two kinds of codes that we're going to create. There's the kana, kana and kanji, and the kana have about, let's see how many there are. Um, so we have. I'm going to include all of these, even though these are not technically kana, but we treat them that way. So we're starting at line 18 and go down to line 287. So 287 minus 18, and then let's subtract these conditional ones, which go from line 31 to 67. And so this would give us 233 codes. Let me make this a little bit bigger. Okay. Not 233 kana characters, but 233 codes. And for kanji, we fixed a bug to figure out exactly how many we have room for, and we do have 250 codes. Also 250 characters exactly. And the reason why there's not 233 kana is because, as you can see in many of these codes, there are two kana characters for a code. And well, that that is so the combinations, like this is fu and a. This is, if you kind of imagine this being like ch in English, it's two letters, but one kind of pronunciation unit, I guess you could call it that. Um, this might be a bad example because it's conditional and it's going to be excluded. So if let's find one that's not excluded. So I guess I don't have fua in included anywhere. I don't know if that's a mistake. Seems like it might be a mistake. Oh no, here it is. So HW no HWA is going to be fa, fu and small a, and so this is it's like this because in kind of in the more basic system of syllables, you just have fu and a as individual as like syllables, and they then in order to get like in order to start writing foreign loan words, they wanted to combine fu and a to fa. Actually, this might not be historically accurate, but if you kind of think of it this way, it makes sense. And there are not any normal Japanese words, only loan words nowadays, at least, that use fa in this case. It's usually originally it was just fu and a. Anyway, so there's others that are not like used for foreign loan words, and that is, for example, like anything. So we have three symbols here: ya, you, and yo. It's kind of it's like a y, the Y sounds. There's ya, you, and yo, and there's small versions of ya, you, and yo as well. Here are the big versions, and here are the small versions. And the small versions attach to syllables that have some consonant and then e at the end. So like ki, shi, chi, mi, they can all be attached to a small ya, you, or yo. And so you can attach a small chi to a small yo, and it becomes cho. And that would look something that should be in here somewhere. Um, it should have been T9 as the code. No, that's not it. Uh, Here it is, TYO. T9 is actually the code for the other system input system I created, which I'm not satisfied with. So cho is TYO, and so that's kind of the gist of it. The main purpose of why I went over that all is to explain that there are 233 Kana codes, but not 233 Kana characters, and um, and I'm in visual mode. Okay, so the other thing is that there are these kind of exceptional characters. These are actually kanji, and these are numerals, kanji numerals 1 to 10. And the idea I have here is that shift and a number will be that number in kanji. So shift 1 is exclamation mark, and that's the number 1 here. Shift right parentheses is 10. Well, that's kind of exceptional, 10. So shift and right parentheses is the 0 digit, but we've got to make it 10 because the kanji for 0 is not really common enough to justify giving it such a short code. 10, the character for 10 is probably more useful. So then we have 2 through 9, obviously. And there you have it. So the mapping is going to consist of these Kana codes, about 233. I think I might be off by 1 or 2 here, and by these number of kanji. And so these so that's actually not totally true. So there's 233 codes without caps lock, and then there's going to be a few more with caps lock to give you the katakana. So most of these characters here are all hiragana, which is what we're going to type with lowercase letters, and the katakana will have caps lock. And so I have a system whereby I kind of indicated that if there's a 1 in this field, this is the auto katakana field, it means that we're going to duplicate it with caps lock and convert it to katakana. And that can all be done kind of algorithmically. You don't need to hard code it. You can kind of do a mathematical operation on the character code to convert from hiragana to katakana. So yeah, so we have a few more with caps lock, and I think that the ones with caps lock are all in here. So let's try and get a kind of calculation as to how many katakana codes there are. So we'll do sed romaji.c, and we will what we're going to say is we're going to print out a certain line range. And so we start with this one, 29 to 287, just to print that range. Okay, that didn't work. Oh, because we need to say print command. All right. And that ends with the chong here, the vowel extender, and we don't really want that one. But anyway, what we can do is we can remove the ones that have a 0 in the last field, right? And so what we also want to do is remove anything that's an empty line and remove anything that starts with a preprocessor thing. And we also want to subtract, what is this? We have 1, 2, 3, 4, 5, 6, 7 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 17, and 5. That is 27. So we want to subtract 27 from this count. So 241 minus 27. And that will give us 241 minus 27 is 214. So, so 214 with caps lock. And so we should have 447 in total. Right. And now there's a catch here because with kanji, we're probably going to allow you to type the kanji in with caps lock on and just give you the same kanji. Like if, for example, if B, C corresponds to some random character like, I don't know, like this. What's a simple one? So if BC corresponds to this one, which is usually used as a counter for a kind of a generic counter, like you would put this after a number to indicate the quantity of some physical thing. And so then that means BC also equals that with capital letters. But don't count that for now. We might not, I don't think we're going to get to that feature tonight where we automatically capitalize the code and get the corresponding kanji. So for the romaji, it's relatively simple. We kind of go through this list, and if it has a 1 in this last field, then we're going to convert it. We're also going to add a second code for katakana, and otherwise we'll just add the exact code literally that it has only. So, all right. With that being said, the kanji are going to be a little bit more complicated, and I wonder if we should just go ahead and code the romaji part now, because that alone is non-trivial and it requires some kind of a little. It might have some tricky math in it. I'm not quite sure. I'd have to get to the details first. So yeah. Let's see. I think that what I want to do is I'll go over the stuff, the kanji part. So so the source for the romaji is from this file, this database, and the source for the kanji is in kanjidb.c, and the place where we actually interpret all like kind of extract the kanji db is in the last rank contained command, which we're going to have to refactor out into a separate file. And this last rank contained command, let's look for what we actually want to pull out. So if you to just review, if we run the last rank contained command, it gives you, I'm putting it separate window, it gives you this, it tells you for every single first character in the code what the kanji will be that correspond to codes that start with that character. And so if you kind of think about this simply, you're going to go to the kanji code, you're going to get all the like all the codes that are not consumed by romaji, and all the ones that start with 1, you'll assign them to codes. You'll assign those codes to these kanji. and and then you'll just do that for the other characters on the keyboard. So and so yes, so this is like the original source for the kanji, and the place where we pull it out is in last rank contained, and it looks like line stats might have what we want. So we have, let's see, construct kanji entry. That might be it. So kanji entry corresponds to lines in the database over here. So we have for E, you give it a kanji key count. You give it an index going up to kanji key count, and then you get a pointer to one of the entries. I'm not sure why it's, oh, because this corresponds to a single line, so that makes sense. So yes, you have like these keys that this corresponds to the second character, essentially, the second character of the code. That might be one way to think of it. But the thing is, these kanji aren't in arbitrary order. So apparently, the way I was thinking is that the last kanji can be kind of the for every like line in that output that we just looked at. For every line here, we can, let's see, for every line, what was I just going to say? I forgot. So yeah, I've lost my train of thought. So let me take a quick break because I'm being distracted by something. Okay, let's try again. So I was saying that for every single line in the output of last rank contained, we are going to take the character that corresponds to the code prefix for all the kanji in that line. So for example, for 1, we're also going to get the free kanji keys that start with 1, and we're going to assign them arbitrarily at first to all the kanji in this line. And so for the purposes of the first version of this command, we are going to just take 1, 1 and assign that to this character, which means person. We'll do 1, 2 and assign that to this character, which means issue is a way you could translate it. 1, 3 would correspond to this, which means go in, and so on. So yes, so this is going to be hopefully it'll be relatively straightforward. So we have the make map kind of boilerplate, make map.c, and yes, this is definitely boilerplate. It's only 5 lines long, and we have romazi.h, which will give free kanji codes. And well, we don't really want, so what we agreed on was that we would do the romaji first, the kana codes first. And so let's look and see, is there a way to get that array? romaji.cc. So we have romaji entry. So apparently no, there's no direct access to these characters, and we'll have to create an accessor, I guess. But it might be better to actually generate. Yeah, let's just generate these things. So we'll create a function which you call, and it would be like void get romaji codes. Okay, and this will be a code array. Well, it's a map array. It's a mapping array, right? And every entry is a code to a string. So it's a mapping of strings to strings. So we'll call it a key mapping array. Key mapping array. And I don't know if we want to expose this kind of, yeah, let's just do it that way. So we have struct key mapping array, and we have struct key mapping element, size t count, size t alloc. Okay. We're doing this based on the previous array the array type that we've already defined, and it's actually a dynamically sized array, as you can tell by the extra fields. Okay, so now we also have to define struct key mapping, and we'll say car key code, I suppose, and this has at most, I think this at most can have 3 letters. 3 characters in the left side of the mapping. Yeah, it looks like I aligned it as if everything can only have a maximum 3. So I'll just add an extra character for the null terminator, and let's see. We want the romazi characters that correspond to it. And so we're using UTF-8, which more or less means that every single character, whether or not there's a small kana in the second index, in the second place of the string, every character will correspond to 3 bytes. And I think that we only have 2 characters at most in the romazi, or the kana part of the mapping, the right hand part of the mapping. And it looks like, yes, I did align it as if there's only two characters. So 2 times 3 plus 1. 3 for 3 bytes in UTF-8 for a character, and plus 1 for null terminator. So 2 times 3 plus 1 is 7. All right. And yes, so that looks fine. So this looks like a good API to me. Let's grab that, and I'm going to go down, I guess, and paste this here. All right, and we're going to go through the romazi array, and we have an array length called nr, romazi nr here. So the name of the array is romazi, and the name of the entries is romazi entry. Okay, so we say size ti, and for I equals 0, I is less than romazi, number of entries in the romazi array. And we also have a codes array. We don't have to initialize it. The caller should have initialized it. And these arrays are trivially initializable. Just set it all to 0, all the bytes to 0, and it will be useful. So yes, so now we have romazi nr, and I don't remember exactly what fields that it has. So let's go to romazi.c. Right, so I have original, converted, use as is, and auto katakana. Oh, so I'm now I know that no, I was going to say all the strings are actually statically allocated, but that's not true, not for the katakana converted ones. So I was going to say maybe we could change all of these like inline char arrays to just be char pointers. And that would be a little bit more efficient. Or would it be? Because the pointers are going to be 8 bytes, I guess. So maybe they wouldn't actually be more efficient. So we have, in any case, we can't use statically allocated strings for the mapping, the generated mapping. All right. So we have the romaji I dot. Oh, what was the other field? Use as is. Use as is means so yes, so use as is. Before I suggested that everything would be use as is equals true, but that's not going to be true necessarily. So we need to say, we need to check if it's use as is true or not. So the purpose of use as is that we can set it to 0 and then set auto katakana to 1, and then it will not include the hiragana version of that mapping. And yes, so use as is. If that's true, then we're going to do this. If it's false, we won't do anything. We also need the auto katakana one. Okay. And this looks fine so far. So if it's use as is, we're going to add a mapping, right? Alloc, what's it called? Alloc grow by, or array grow by, I think. Grow array by. There we go. And we set the array codes. We have to dereference it. Codes grows by 1. Was it only 2 arguments? Edit util dot h. Grow array by, yes, just 2 arguments. Okay, grow array by, and then we got codes dash l codes dash count equals. So this is the last item, count minus 1 dot key code is going to be set to, we're going to have to use a string copy function or whatever, equals codes dash, romaji I dot orig. Okay, so we need to use the string copy function, I think is what it's called. Stir and copy. I guess we need to use stir and copy to be safe. The strings may not overlap, and the destination string must be large enough to receive the copy, and some byte source are copied. N bytes of source are copied. Okay, so when we call stir and copy, we set it to this, and the size is size of codes. This is hard to reference, so I guess I need to do codes dash l dash key code. Right. Okay. So this gets the size of that key code, and it's accessing the 0th element by doing this, but that's fine because all the elements will have the same size for the key code field anyway. So that's totally fine, even though it looks kind of ugly, I guess. And then the source is that nomaji.orig. Okay. Right. So I think I'm gonna have to create a new function to like make this manageable, because I don't like the way this is indenting so much. And we also have to copy the same thing to the other field, which was the romazi. Oh, this is not correct. I shouldn't call this romazi. I should call it Kana. And Kana. Okay, and this gets set to, well, the size. First we have to specify. What is it? It is Kana, right? And source data is in conv. So let's use the same name. Instead of Kana, we'll call it conv. That way these two will have a similar. And let's also call this orig. That's better. Now the naming for this structure maps the naming for this structure, which is great. So we call this ridge. We use the same name there. And this is conv, not Kana. Okay. And that's fine. That is all done. The use as is branch is fine. So now the auto katakana 1, we're also going to have to go array by. All right, that's obvious. And I'm already kind of not happy about the fact I have to indent this. So okay, I think that we want to copy this. Like the first step of copying is the same for both branches, because over here we're also going to do the stir and copy, but we're going to have to, but just after we copy it, we're going to convert the characters. We're going to convert orig to be capital letters and conv from hiragana to katakana. So let's go and create a function for that. So we'll say void, static void, copy to mapping, and the source would be, well, let's do the destination first. It's called struct key mapping m, or let's call it dest. Maybe just copy mapping, because really both of these pieces of data are mappings. Construct it's called the romaji entry source, and we're over 80 characters. Let's call them just D and S maybe. Actually, let's not do that. Let's just indent it, make a new line. And okay, so we just take this. Let's put this back here for a second, and the way we call it is copy mapping codes dash L codes dash count -1, and the source is romaji I. Excuse me. Okay, and here we're also going to do the same thing down here. Well, either way, we have to grow the array. We could put that in the function as well, but I don't know. Maybe not. Yeah, I guess we probably should. Well, let's do that a little bit later. Let's wait until we actually have it working first before we micro-optimize our like line length, or line count rather. And so here, now we want to convert the left side from uppercase to from lower to uppercase, the right side from hiragana to katakana. Now the lowercase to uppercase is going to be easier. It's not going to be locale sensitive. Like we're not going to like treat the Turkish I properly, where like we distinguish between whether the capital I has a dot or doesn't. We're not going to do anything locale sensitive. We're just going to do it as far as English is concerned. And let's see here. I'm wondering if everything is a lower when we're doing automatic converting uppercase, if we already have like everything is already all lower letters. So actually, it looks like these lines, we do have non-letters in there, and we don't want to convert the 7 to uppercase, right? So that's important to keep in mind. Okay. So, all right, now we're going to get a car for, yes, this char, and this is going to be like the index into the left-hand side of the mapping. So we call it like source, I suppose. No, it's called, what's it called? Orig. Orig equals codes dash L codes dash count -1, and it is equal to orig there, right? So we start in there, and we do while orig, and at the end don't forget to null terminate. Or we could just, oh, we don't have to null terminate because go by already zeroes out the new entries. We made sure of that earlier. Okay. Now, orig, so if orig is greater than or equal to A, and it's less than or equal to Z, then we are going to change it to be uppercase. So orig or equals, now what is the, I think we have to actually turn off a certain bit. What was it? Man ASCII. So the difference between, no, we can just do this kind of more roundabout. We can just say the difference between A to A is going to be 1 bit, because the difference between these two is only 1 bit. I think it's 64 actually, now that I think about it. Or maybe it's, no, it should be 32. So over here, lowercase a, the hexadecimal is 61, and uppercase A is lower than that, has a lower index, and it's 41. So it's 20 in a hexadecimal, which means 32. So we are going to just do right. Oops. Where's my cursor? There. Okay, so that line will have the effect of setting it to turning it into an uppercase letter. Now we have to do the same thing for the hiragana. And excuse me. Now this is more tricky, but the good news is that I already wrote code to do this in Perl, so I'm just going to crib off of that. So let me start a new, let's not start a new window actually, let's use this one. So I'm going to go here, and I should have the source code for my other project here. And this is, maybe it's in read codes. Read codes and process lines. So process lines, this is processing the database of codes for the other input system. And I'm not going to go into too much detail explaining this code because we're really only interested in how to convert the hiragana to katakana here. And so shift map, that sounds important, although it's just talking about shifting for the punctuation, so maybe not. Where is shift map used? Shift last char? No, that's not what we want. So Yeah, we shifted the last character. In this old system, we shifted the last character of the kanji input code, and then you could use that to input a kind of minor variant of that same kanji, and that's not what we want to do here. So process lines, I think it might not be in this stuff. Let's look in expand codes. Maybe that's it. Expand codes. Oh, this is different. This is for generating a kind of an external database format for conversions. So let's see. But I think this might have the conversion, like the conversion to katakana logic in it. Output codes. So yeah, this shift just talking about different encodings for Japanese. Unshiftable keys. Output codes. Output codes. Code. I don't actually see the conversion logic here. Let me make sure that it was actually converted dynamically. Less Kana. Yeah. See, this code file is very short, and so there's some place where we should be actually actually doing the dynamic conversion to katakana. Maybe it's in code map. Oh, that sounds right. New key to number, finding process register later, increment key, number to key, write code, register, lookup, register auto-generated codes, code by kanji, register auto-generated. Oh, auto-generated is probably what we want. Register katakana in caps. That sounds important. Where is that being used? Self-write code. Here. Actually, this is very kind of obfuscated, I guess, unless you know exactly what TR does. So this means that so this is apparently the lowest hiragana code, and this is the highest code, and this is the lowest and highest katakana codes. And these are actually unusual looking. These are not the normal sized a and ke. This is like smaller versions. And so anyway, these two ranges should be the same size. And this TR line is a lot like just is very similar to just saying TR A to Z, A to Z. I believe that's how it looks. So what we got to do is we got to figure out what number to add to the hiragana and katakana, to the hiragana code to get katakana, and then we need to make sure we do it in UTF-8 in like the individual bytes. So we're interested in these characters, right? So let's get the hexadecimal representation of these. A and K and A and okay. So we're going to echo that, or maybe printf so we don't get a new line, and do a hex dump. All right, 3. Let's put spaces in between there so that we kind of get alignment. All right, so we don't have to worry about. So it's a little bit easier to see the separate characters. So E3 8181 for the lower hiragana range, lowest part of the hiragana range, then E3 8296. Okay. But this is probably little. No, there's no endianness here. So, because this is UTF-8, and then 82 to 96, and okay, so if we take 81, 80, no, start at the end, 82, 96 minus 81, 81, we should get the same thing as the other range, right? It is, okay, so the first byte is always E3, which is easy to remember for even for the katakana. So B6 minus 83. B6, no, 83 minus A182. 82. Right. And maybe we can do this in our heads. So 96 minus 81. Okay, so actually you don't have to do any carrying to figure this out. So it's 1. So the digits are 0, 1, 1, 5. 0, 1, 1, 5 for the first one. And the second one is, oh, this is harder. So it's actually, oh, this looks like it's not the same range. B6, A3. Oh, because I copied the characters in the opposite order. 83, B6. I was reading it backwards. And 82A1. Right. And this is 115 as well. Okay. So the first byte has to get 15 added to it, and then that may have to be carried over to the next byte. And so to kind of state more explicitly what we're doing, so add 0 by 15 to the lowest byte, and then add 0 by 01 to the second lowest byte, and then you're not going to have to carry, right? There's no carrying involved for the last byte. The first byte, the most significant one, is always E3. So first we need to actually see if it's in the range. So there's two parts of the problem. First, we have to make sure that it's in the range that we want to actually change. And the second is that we want to actually apply it. So what we can do is So the Intel systems are going to be opposite endian of this, right? So we can actually use the network byte conversion functions to convert from this to like the one that we can actually operate on mathematically. And I think it's called like N2HS, H2N. So if it's a L, H2NL, convert values between host and network byte order. Converts the unsigned integer from host byte order to network byte order. So network byte order is the sensible one. I think it's called, I don't remember, I get the big and little mixed up a lot. Let's just clarify that now. Big endian versus little endian. Big endian has the most significant value stored first, which is how UTF-8 works and how the network byte order is. And the little endian is what we might want to convert to if we're running on Intel or if we're running on Intel. So we do want to use H2NL. Well, it's host 2. No, actually, well, H2NL and N2HL are the same thing because they're just doing the same. They're like doing, because converting from big to little is the same as converting from little to big. But anyway, if we consider UTF-8 as N, the network byte order, then we got to use N2HL and then H2NL to like pack it back. So let's include this ARPA/INET. Okay. And so what we'll do is we will take, yeah, how are we going to handle this? So conv is 7 bytes. And that's because, all right, because yes, because it's only, each character is going to be 3 bytes. So that makes things a little bit more complicated. So let's create a function which does this so that we can think about it a little bit more easily. And we'll say convert hiragana to katakana, and we'll give it a string. And that is codes-l codes-count -1 and conv. And I don't like the way we're always referring to this codes thing. Let's do struct. I just had an idea about how we're going to convert this to a function later. This is going to be simpler later on. It's going to be complicated when I'm typing it, but simpler later. So hiragana to katakana, and okay, static void hiragana to katakana, and we got a char conv, right? Okay. So while conv, because we're going to stop at the end, stop when it's null terminated. Now, can we assume that it's going to be 3 bytes, or are we not actually sure? I think that we can really be pretty sure that's going to be 3 bytes. Because, in fact, we can even be sure that it will be in range, to be honest. We can be sure that's in range because I don't have any like non-kana in the conv section if I'm also setting the auto convert to 1. Now I may have non-kana in the right-hand section of the mapping for here, but in that case I'm not setting auto katakana to 1 anyway. Then again, I might have to worry about this because this is going to have to be converted to uppercase. Oh, this doesn't have uppercase. Never mind. If caps lock is on or off, this is only going to have 1 code because it's not a letter in the left-hand side. Okay. So we can assume that it's 3 bytes and that it is kana, and that makes things a little bit easier. So we'll just say we'll grab the we do want the 16-bit, don't we? Because 3 times. No, we only need the last 2 bytes, second and third byte, right? And that's a short. So we'll just say ch, call it kana. We'll call it lower 2 bytes. Low 2 bytes equals conv 1 and bit shift left by 8 plus conv 2. I'm trying to go to the 8. Why am I not able to go to the 8? Plus conv 2. Okay. And this is already actually in the right endianness. So I've already done the conversion kind of implicitly. So we got the low 2 bytes, and we're going to say low 2 bytes plus equals 0 by 115, right? And then we can do conv 1 equals low 2 bytes 8 and conv 2 equals low 2 bytes. Right, and the conversion will automatically chop off the upper 8 bytes, or the upper 8 bits of this low 2 bytes variable. So then we got to do conv plus equals 3. And that should be all, actually. That should be fine. So, I was thinking about simplifying this code even more, but maybe that's going a little overboard. I think this will work. I could be wrong. So let's start writing this make map thing finally, the make map command. We need romazi.h. We also need include commands.h because that has the file handles that we actually want to write to in order to make this testable. So we got let's declare the array where what's it called? The key mapping array. And we'd call get romazi codes, and we didn't actually give it a name, just of codes. And now we got to loop through them. So size ti equals, so that's the loop variable. For I equals 0, I is less than codes dot count I plus plus. Okay, then we do xf printf and out, right to standard output. We have the left hand side and the right hand side and a new line. Left hand side is in codes.li.orig, and then the other side is codes.li.conv. I think that's all we need to do, really. Let's make sure it works. Make. Okay, got some errors. Codes is undeclared in romazi.c. I already have that open down here. It is on line 453. Codes is, alright, it's called dest, not codes. Dest, I never actually fixed this. Dest dash orig, right? Size of dest dash orig. And then so that's a much nicer looking size of invocation. And then romazi.orig. Yes, that seems right. Romazi. Okay. Just checking the name of the romazi thing. And so here we've got to do delete to O. Dest dash conv and size of dest dash conv, and then oops. Okay. And use the wrong name here. Dest, here, dest. And then what's the next error? Get romazi codes incompatible type for argument 1 of copy mapping. Expected struct key mapping values type struct key. Oh, I got to get the address, not the value. Copy mapping. So down here too. Okay. Same error as the next one. 450 expected const but got struct. Okay, so the other one also has to be address. All right. And let's just rebuild, even though there's still going to be errors. Copy mapping, IN declared. Oh, because I didn't. Source dash orig. source dash. Okay. Size of makes pointer from integer without a cast. Oh, I got the order wrong, huh? The size is the last argument, isn't it? Okay. Make map, conflicting types for make map. C. Ah, order is wrong. And delete. Make map.c. Make map.c, previous action make map was here. Commands.h, conflicting types. Why is it still wrong? Make map. Oh, because it's not const. Okay, good. Now if we run make map, it should basically work. Or it'll just freeze. Make map is freezing. Interesting. So maybe this loop is freezing. We do add conv plus equals 3. So it may be just looping this infinitely because maybe conv is not null terminated properly. Copy mapping. Oh, over here we don't actually add orig plus plus. There we go. Okay. I guess this orig thing might be better off as a for loop. Oh well. I'm not that passionate about for loops. Okay, this looks promising. Well, it's wrong. I mean, this is an equal sign. Why is that an equal sign? And it looks like this, the left-hand side was capitalized, but the right-hand side was kept in hiragana. And ro is getting, that's ah. This is ah, but the left-hand side is ro, which is wrong. Okay. Go right by. So this is kind of confusing. So why is it not even maintaining the original, the as is mappings? Why is it even screwing those ones up? That's a mystery for now. So let's just see what the first one it screws up is. It is looks like it's this, because this is not katakana. The right hand side is not katakana, but the left hand side is capitalized. So what is going on there? Use as is, auto kana. Oh, here we go. Because this is not right. Orig is being set to the previous element. So this really does ought to be a for loop. Orig equals codes. Excuse me. So this really did cause a lot of problems, didn't it? So what we can do here is we can actually just say if it's not katakana, then we'll skip the rest of the for loop body. And that way we can actually unindent this, and we'll get some more room and less wrapping. Yeah, that's better. Now this has to be put up top, unfortunately. And okay, let's try it again. Okay, so now the as-is lines are correct, fortunately, but the katakana ones are still wrong. So this F, this J to chisai tsu, to small two is correct, but it looks like it failed to convert tsu to the uppercase he, or it failed to convert tsu to uppercase tsu, and instead it converted to this other character, which is he. And can't even tell if he is katakana or not because this is the one character that looks both the same in katakana and hiragana. But it looks like F, this one was converted to katakana correctly. But this was not. This is both wrong, the wrong character and the wrong casing over here. So, now the first byte was the same. The first byte never changed. But the 2 bytes after are the ones that do change. And we are adding the first one. Does this have to be cast, maybe? Maybe this has to be cast and then it's going to work. UN16 type. Let's see if that changes anything. Either way, I think I would like to cast that because it's not obvious that it's doing the right thing. Low 2 bytes plus equals 115. Yeah, this is confusing. Okay. So let me look again at the hex dump. Okay. So E3 is the same, always the same first byte. 8181, E3 82. 8296 rather. 8296. So it's adding the second byte shifted by 8 and adding this is maybe char is unsigned, or it's signed rather, that's why there's a problem. That might be what's wrong. I bet that's what's wrong. 2 bytes. If I just do this, maybe that would be good enough. Almost. Looks a little bit better. I mean, these are still wrong, but they don't look like that wrong anymore. That did make a difference. So even if conv1 is signed, that's fine because we're just going to shift left by 8 bits and drop off all those upper bits which make it negative. Low 2 bytes plus equals 115. Then we take the bytes back. Okay, so why don't we do this? We're going to print to standard error. We're going to printf error. First we print what we're converting, and after that we print what we're converting, and then when we're done we're going to print the actual like converted the the numeric conversion of it. %s, I guess. No, short. What is short? D. Oh, because the 16-bit variable will be converted to an int. Short will be converted to int automatically, I'm pretty sure. And let's call this hexadecimal. And that will kind of give us some insight into what's going on. We'll know if that's actually being converted properly. Error is not declared. Where is error declared? util.h maybe. I thought it was in commands.h, which we're already including. File out error, yeah. Romazi, let's see. Oh, because we're not including the utility. Okay. I don't want to start including it now, so let's just change this to use the normal stuff. Okay. Okay. So let's see if this one is correct. We're going to do echo this guy and hex, convert it to hex. So this was converted 81A3, 81A3, AO. Oh, right, because that's a new line. OA is a new line. 81A3. Oh, I know what's wrong. So this 115 is actually the size of the range. It's not the difference between hiragana and katakana. So that's why we screwed up. So let's go back. Let's do this printf thing we did before. We got to actually find the difference between this and this right? And that will represent what we're trying to the stride of these two sets of characters. So it is 8. So this uppercase, the katakana for is this 82A1, 82A1 minus 8181. Okay, so that's equal to 1 and then 2, 0. Okay. Now that should be okay. Sort make map. Okay, great. This actually is, I'm pretty sure this is correct. This seems to have everything we want. Okay. Great. Now we probably want to start writing the test for this. And how are we going to do that? Well, let's review this and see if we want to simplify the code. Actually, writing the test is probably better. So let's go here. Let's see what are we going to call the test? Last rank contain test, rank coverage test, romazi test. I think we kind of want to call it make map test because it's eventually going to have all of the kanji codes in it. And well, no, it's probably better to test the romaji separately. Let's just edit romaji test.c and yeah. This is kind of annoying though because then we have to make map, edit make map.c. Because I don't want to have to write this stupid line again, but maybe I should just deal with it. I mean, really, it's not a big deal. The alternative is to, cause I don't want to have the, the alternative is to test the, either test the kanji and the kana all in the same test, or we can have make map optionally and exclude the kanji. And I guess I like the idea of make map excluding the kanji in the long run. So I guess we'll go that way. So we're going to make a new test called the make map test after all. Make map test, make map test.c. Okay. Make map test. I think that's all we need to do to make a new map test. Edit make map test.c, and we're going to base it off of the romazi test. Commands test util romazi mapping, and we're going to call make map with no arguments, and we're going to have end test, right? Okay, looking good so far. Now let's actually give it the wrong stuff here, the wrong expected results for the test, and make sure that it fails first. And we're not running the test at all. Okay, let's actually move this so it's in alphabetical order. Okay, here we go. Yeah, so it's correctly showing that the entire file is missing in the expected results. All right. Oops. And make map test. All right, so we'll do new sort make map and save it to X. Then we're going to insert this here. Oh, it didn't take care of the kanji yet. I'm not sure why it's showing mojibake here. So let's do something else. Well, less /x. Yes. Why does it show that? Why are some of these characters incorrect? I mean, it shows up correct in the console, doesn't it? No, not unless. It shows up correct here. So I'm not totally sure why that's happening, but I don't believe it's my fault. Let's just copy it this way. Okay. But now it's not handling the tabs right. So let's see here. We want to replace space and more spaces with one or more consecutive spaces, two or more rather consecutive spaces with a tab. No, it didn't work. I guess that's because it's like the non-extended regexes by default. So we want to do space star, because 2 are required and 3 or more are optional. Okay, good, that worked. Oh, but this did not work. Ha, hi, ha, he, fu, he, ho. That didn't work. What's wrong over there? That is a mistake. Oh, it looks like there's some other mistakes here. This is not all fixed yet. DYE should be like, should not be this. That's not correct. Maybe it is. It looks like for some of these dual, yeah, the characters with two in them, with two in the right side, two characters or two kana, it's only preserving the second one. So I'm glad we found that. Let's delete this. These are not correct yet. So edit romazi test. No, I don't really want to do that. Actually, we want to go to romaji itself. Now, why would it only preserve the second character? That is interesting. We'll do some printf debugging, I suppose. Standard error, print. So we might want to make sure that it's actually this loop is going over twice, is being gone over twice, and not only one time. That would probably help. Why is there blue here? Well, I don't know what that's about. Okay. So I'll make again. This doesn't look right. It looks like it's skipping a lot. Looks like it might be skipping the first character. Or rather, it's giving us an empty space. Basically, Terminator. Well, that's because there's nothing there. Oh, that's because we're adding the conv before we print it out. Okay. Looks like we are doing it twice. Let's go to romaji.c in a different place. So let me make sure that it's consistently doing the right number of characters in each iteration. Romaji mapping 0. Okay, so for this 2, it looks like it's not getting anything. Nothing is there. Okay. So let's also print out the low 2-byte value. Put it on the same line, but on the left-hand side of the converted string. Let's print out the converted string as well. or the pre-converted string rather. Then we do also the post-converted lower 2 bytes. And a little indicator to indicate direction of conversion. But it's not in hexadecimal. That's going to be harder. Let me do it in hex. Okay. 81. 81A1. So it looks like a lot of these are working, but some of them are not. Chi. A2C1. Maybe I need to maybe I need to figure out what the real codes are. So Unicode. So hiragana Unicode value. Where did I put it? Okay. Okay, this does not have katakana in it. Hiragana 3041. So small a is there. And it goes up to, should go up to small k, right? Small letters, voicing marks. 309C. Oh. No. No, that's not it. Now I'll do another search for katakana Unicode. Katakana Unicode values. 30A1 and 3041. Is that the right difference? 30A1. Oh, maybe this has to do with the fact that it's UTF-8. That might explain it. It's UTF-8 and I don't understand how the math works. Oh, it's probably not carrying properly. That's what's going on. It's not carrying properly. Okay. UTF-8. See, because UTF-8 works by putting bytes, by essentially having in the second byte, the first 2 bits are always a certain value. Actually, for the second, third, and fourth bytes, the first 2 bits are always 1, 0. And so that means we can't just carry normally, because that means this may end up getting set to 1, this byte, which is always supposed to be 0. And so what we've done is we've been taking these 2 bytes, we're not handling the first byte in this, but we've taken these 2 and we are kind of we are apparently setting this to 1. And I believe that's what's the problem. So I think what we want to do is we want to see if this is 1, and if it is, we set it to 0 and then add it to the second byte. Add it to byte 2. So I believe that's all that we have to do now at this point. So if the third byte has 40 turned on, which is the second to last bit, then, and of course this was most likely why the text editor didn't know that it was actually text and thought it was binary. Then conv 1 plus equals 1. TF8. Okay. Okay. Still see a lot of zero, like empty. Wow, it didn't actually fix what I was hoping it would fix. It didn't actually change this. So this character is still not properly being converted, unfortunately. Oh, because doing it at the wrong time. Here. Before we pack it back up, we have to actually fix the carrying. Load 2 bytes. Conf. No, it should have been fine to do it where I was doing it. Right? This should have been fine. Oh, but I was doing it after we printed it out. That's why. Okay. Okay, great. Now this is looking correct. This actually isn't. Excuse me. Oh, because this is only converted the first character, but down here, it's converting the next character. Okay, so this should finally be correct. I'm going to take out the debugging commands. Oops. Okay. Now we're going to add the actual output to the romazi test. Oh, yeah, it was in the make map test, rather. Read the test out. Temp expected WQN. Oh, not the expected. We want the actual make map test. Okay, good. So now we're going to go down. All right. And then we want to add a quote at the end of each line. There's probably a correct way to do this. I guess with macros is the right way. So I'll do QA, go to add to end of line, quote and comma, then exit this and go to the next line. And then end. Okay. So now we want to do at A. Okay. And how many lines do we want to do? We want to do... oh, we already calculated this, didn't we? It was like 200. So we're going to do 200 at A. Still a lot more. What was it? What was the actual amount? It was 447, I guess, if you include the caps lock. Okay, let's do another 200. Alright, I'm not sure if I was way off or just a little bit off. Should only be a little. How many lines is this? 378 lines. So why was this so far off? 447 I thought it would be. Because there wasn't maybe the as is. There was some as is codes, not as is codes that I included. Yeah, because of these ones. These ones were wrong. So these are not included as is in the mapping. These are only converted to katakana and then used. So if we, yeah, so the correct number is more like 300 something. I'm a little too lazy to actually give you to actually do the calculation and confirm that we're correct. I am pretty sure it is. So now let's try and run the test. Expected expression 3. Oh, I actually don't want commas, do I? I want new lines. And I guess I don't want, yeah. I guess you can't have trailing commas on the last argument in C. At least not in the C settings I'm using now. Comma with. Okay. That looks right. Two. Comma A. Oh. So these codes actually have a comma in them. That's why. Okay. Too many arguments. Doesn't tell me how many it thinks I have. Ah, I see. Okay, good. Looks like the test is working now. Alright. So we've generated, excuse me, the romaji codes. I thought this would be the easy part, but it's not. So anyway, we have, let's see here. We have any simplifications we can make before we we kind of commit this, because now that we've written the test, we can actually make simplifications and be comfortable about it, that we're not changing behavior. So we do have these two lines repeated, but I don't know if there's a simple way to really make it better. Like, we can have the function grow the array, but I don't know if that's better. Yeah, we can just call this add new mapping. Add converted. Copy. How about append copied mapping? And we give it the array. We call it struct key mapping array codes. And then we say grow array by codes grow by 1. And we change des to codes dash L codes dash count minus 1. Okay. And then we paste it down here as well. And copied mapping. Okay. Now maybe we don't really need this extra function because we're only calling it once and we are not that far indented. But then again, it may be nice to just have it. I can't think of a good reason to add or remove it, so we'll keep it there. Handle carrying in UTF-8. Yeah. Okay. Okay, I think that we should probably take a break for now. I will make a commit with this stuff and push it, and then I will start again tomorrow or the next day. Thanks for watching. Okay, I realize I forgot a few things, so um, there we go. So we didn't actually free the array that we allocated in the make map command implementation over here. And I remember, so this is the array, and I remember that I was interested in making like a free map macro that would actually zero out all of the fields so that you don't actually get a dangling pointer. And I still feel like I want to do that, so I'll just go ahead and free it here, and write the new macro as well. So I'll call it free array, and we'll just give it codes dereferenced. And because everyone knows it's a macro, so don't bother using pointers because everyone knows that we're not really calling a function. Free array, and the array is here, and we will say array dot L. So let's write the code to actually zero everything out. Array dot count equals 0, and alloc equals 0. Okay, and also of course we need to free it. Array dot L, right? Okay, and so that should be fine. Let's just run the test one more time. No, something's wrong. Free array. Oh, forgot a backslash here. Okay, try again. Test origin, test undeclared. romazi.c. C. I have a error here. I didn't know that. I thought that this was compiling already. Append copied mapping, size of codes. Codes destination, right? Dest was the old name for that argument, or the first argument, which is now a different argument. Codes dash. Right. Dash L 0.rich. Okay, try again. Okay, good. Now, let's just review what we've done so far. So we have we added a new test for the make map command. That's the first thing. Then we also implemented the make map command here, which is very trivial as far as the command body itself. It's just calling a function which does all the hard work. And then we have the test, which has the golden test output saved there. And let's go to the end of that. And we implemented the make map stuff itself. It has to do the hard part is converting the Kana to uppercase, and then we wrote a utility to free array, and that's about it. I'm going to commit this here. So we'll just keep this simple. Implement make map command. Implement Kana generation in make map command. Don't need the word implement. That's kind of redundant. And so yeah, I don't want to say a whole lot here. I think that's just fine for now. I will translate this into Japanese and after I finish recording. And anyway, thanks again for watching.